Alright, hey ISTA 100 students. This is Colin, one of your TAs, and I'm actually going to go over and do a little bit of review because a lot of you came to my office hours and a couple of weeks ago, since we've had them, and I was able to help you out, but I kind of wanted to go over the regression and mean because a lot of people made similar mistakes on homework 5. And I figured I'd make a video so that you don't actually have to come to office hours because they're unpredictable and it's hard to actually make it in. So on homework 5, and I'm going to cover these concepts of regression and using averages to make predictions. And I'm just going to use the same data we were given for homework 5 because it's pretty simple and I couldn't think of anything better. So basically, in homework 5, the first 3 problems we're given a long problem that deals with the heights and weights of 6 different individuals. And in the first one, we're just given the weights and said, hey, so we know that these 6 people, they weigh 136, 149, 145, and so on. If you were going to predict how much a 7th person would weigh, how could you best do that? And the answer was, well, we're just going to average the 6 people. And we're going to guess based on that. So the average of the 6, the average turned out to be 145.3 pounds. And that's not great because not everybody weighs 145.3 pounds. There's a lot of variables. Men tend to weigh more than women. People who are taller weigh more. People who are more athletic might weigh more. There's a lot of variables that this can't account for. All we know is that out of 6 people, the average weight was 145.3. Now on our graph here that I actually printed out, so weight, our y-axis is weight. So saying that the average is 145.3 is the same as saying that y is equal to 145.3. And at this point, if you've taken algebra, which I think all of you should have, or you should be taking it, you can draw this line. You can actually graph 145.3, and it is a flat line. When we have no x, like when we just have a y and then over here we have a constant, that's always going to be a flat line. It may be higher or lower depending on this number, but it's always going to be flat. So we just graphed what this is. It is our prediction. And the reason it's flat, it's flat mathematically because it's a constant, but in terms of what we're doing in this problem, the reason this line is flat instead of sloped is because height doesn't matter. If your height is 58 inches, we're still predicting that you weigh 145.3 pounds. If your height is 70 inches, same prediction. Doesn't matter. It's a flat value, always the same no matter how tall or short you are, right? Which is obviously a flawed way of doing things, but we're doing it here just to kind of make a point. So the second problem in the homework asks you to calculate the sum of squared errors. And most of you actually got this right, but basically what we're doing when we calculate sums of squared errors is we're saying, all right, well, we've got this prediction, and then we've got our actual values. How far off were we? And again, what we're going to do here is visually, to measure that, we're literally just measuring the distance of each point back to the line where we predicted, right? So some of them are closer than others. Some of them are way off. Some of them are above the line. Some of them are below. That's fine. We're actually, our formula that we've got on the homework, actually I'll go ahead and write that formula out so that we can talk about it. But our formula kind of gives us a way to compensate for the fact that there's some differences. So our sum of squared errors is equal to 1 over n, and then we've got this big sigma sign, this Greek letter that makes you feel like such a cool person when you're showing your friends all the advanced mathematics you're doing. And then we have x sub I minus, well, I'll tell you what these things mean in a second, squared. So this is our formula for sum of squared errors. And what we're doing here, don't be scared by the Greek. We've already gone over this, but this just means we're going to do this whole thing n times, 6 times in this case because we have 6 people. We're going to do this 6 times, plugging in each person's each sample's individual data each time, and then we're going to square all those and sum them up. So the x here, we use this same formula for the mean and for the regression, but what we're doing here is x is the individual value for weight, and then this funny little guy with the dots over it is our predicted value for weight. So in the case of when we're doing mean right here, we're going to do this 6 times, and every time x is going to be the same number. Every time the x with the dots over it, the predicted value, is always going to be 143.5. Are you starting to see this pattern? 145.3. I guess I'm dyslexic. So we're going to do this math problem 6 times. Each time it's going to be the actual value of x minus 145.3, right? So I've already done that math. I'm not going to make you sit here and watch me do it, but I do need to copy it onto this paper. So this one, this distance right here is our first error, and that distance is actually negative, because remember it's negative because this one's below the line, so it's negative 11.3. And then the next one is negative 9.3. And then we have -3.7, and then we have negative 0.3, followed by 6.7 and 10.7. So these are the lengths, if we were to actually count off tick marks on the y-axis for weight, these are the distances from our prediction. Negative 11.3, negative 9.3, negative 3, or positive 3.7, negative 0.3, 6.7, and 10.7. Now, one mistake that some of you guys made on the homework was that you added all these up and then squared it. That's the right idea, but the order of operations is wrong, because then we have the negatives canceling out the positives, and we actually lose information when we're calculating this whole thing. So what we actually want to do is take each one of those and square them. And so actually, I'll go ahead and do that math for you. So let's write down our 6 values over here. And we have to square all of these, because by squaring them, remember when you square a positive number, it's a positive number, and when you square a negative number, it's also a positive number. So I'm going to do the math on my statistic computer over here. Okay, so I fixed my mistake, and so we've got the squares of all these numbers. Some of them were negative. Now that we've squared them, everything is a positive number. So these are actually the squared deviations, or variations. I forget. Anyways, don't quote me on that. So if we sum all these up, if we add all these together, what we get is 387.34 roughly. Now remember, I rounded these a little bit. So they're not exact. That's okay. We didn't mark you down if you rounded a little bit. So that's our sum, and then we also want to divide this by 6, because remember what we've done here now. We've done this 6 times. We got those numbers. Then we squared it 6 times because it's still inside of our summation symbol, and we got these numbers, right? So now we've added all those up and gotten 387. So now we've done this whole part of the equation, including the big sigma. So now we just have to multiply that by 1 over n, which is 1/6. So multiplying it by 1/6, multiplying this number by 1/6, I'll just write that. 16 times 387.4. And the answer to that is 64.556, blah, blah, blah. Right, so, and so on. So that was our answer to the mean. And remember, what we've basically done is we took all of these lines that I just drew in, added them, or squared them, added them together, divided by 6, and got this number. So this number is actually a representation of how much error is in our, our prediction. How bad it was, pretty bad it turns out, at predicting people's weight. Okay? Now, where's my second sheet?